Welcome everybody, I am Giovanni Francese, I'm a PhD student from the Cognitive Robotics of TU Delft, and today I'm happy to share with you the results of the paper ILoSA, Interactive Learning of Stiffness and Attractors. Which is the goal of this research? The goal of this research is to teach robots how to perform manipulation tasks. And what is a manipulation task? The manipulation task is the change of the state of the environment that is surrounding the robot through the application of forces. Here we have some example of manipulation tasks. For example, the operation of plugging and unplugging, or the operation of cleaning a table, where the human or the robot has to push the cloth on the table in order to generate enough force for cleaning the table. Or the operation of moving objects that cannot be carried, for example, and need to be pushed around. So how do we want to apply a force? The control theory gives us different tools to allow the robot to apply a force on its environment. What we chose is to use an impedance control, and I will explain you later why we did this choice. In particular, how the impedance control works. The impedance control is coupling the end effector and the desired goal of the robot with a spring damper system. In case there is an object between the goal and the end effector position, this will result in application of the force. So we decided that we want to use an impedance controller, but what do we want to learn? So what we have to learn, and this also gives the name of the paper, is the stiffness and the attractors. So we decided to learn not the attractor itself, but the distance with respect to attractor, and then to compute the attractor simply as a summing operation. However, we need to choose a model for storing our data, and we decided to do it with a dynamical system. So the distance with respect to attractor is a function of the current position of the robot, is independent from time. And also the stiffness is going to be a function of the current position of the robot. Now we need to choose how to fit our data. And this is the most important part of the research, because we need to encode in our regressor all the desired properties that we want for our robot. After a lot of research, we decided to go for Gaussian process, in particular for different properties, and one of them is the smoothness, the differentiabilities, and the availability of epistemic uncertainties that we are going to explain later how to use. In particular, because we are going to use an impedance control, we also want the effect of getting compliant when we are in region of uncertainty. And the kernel, the square exponential kernel of a Gaussian process, allows the vanishing of the prediction. And this vanishing brings the robot to have zero delta, so not moving anywhere, and also to have the drop of the stiffness that results in a compliance of the manipulator. After we decided which is the model that we want to fit our data, we need now to decide how to provide this data. We decided to use learning from demonstration, but in an interactive way. So the robot is teach the beginning, the initial policy is provide through kinesthetic teaching, where the human is bringing the robot around and showing the demonstration. In this part, we are recording the points and initializing the model, considering which is the desired delta in each position of the end effector. After initialization of the model, we start the interactive part, where we can give correction through a 3D space mouse. In this part, we're exploiting even more the properties of the Gaussian process, and in particular, we develop a system that is more data efficient, because it's not adding new points to the Gaussian process, but is correcting the previous one whenever the correction is happening in known region of the workspace. This allows to avoid to increase the Gaussian process with unwanted amount of data that will make the training of the Gaussian process that requires the inversion of a matrix and the inference extremely slow. So what we are doing when we are in region of certainty, we are spreading the correction coming from the teleoperation device on the database of the robot according to the equation you see at the bottom of the page. And when we are outside the zone of certainty, we are adding new points to the database. Now that we decided how to initialize the model with kinetic demonstration and how to correct the model in case some undesired or mistakes were encoded at the beginning of the demonstration, we still have the problem of understanding, because we only have directional feedback. What do we want to correct? Do we want to correct the distance, so the attractor distance, or do we want to correct the stiffness? And for doing so, we use an heuristics that simply says, in case the attractor distance goes beyond a limit, we decided to increase the stiffness. So we are obtaining the same increase of force that the robot is going to apply on the environment, but at the same time we are keeping the attractor distance as bounded. As already mentioned before, the Gaussian process is also giving as output a measure of the epistemic uncertainty. The epistemic uncertainty is giving us how much the robot, or better the intelligence of the robot, is confident about the decision to take. In particular, we have an issue every time we work with a dynamical system, that is the covariate shift. So every time that the robot is diverging in region of uncertainty, it will extrapolate. So what we decided is to add an extra term on the dynamical system, that is a term that is proportional to the gradient of the variance manifold. That is easy to compute because of the mathematical formulation of the Gaussian process. In the picture, for example, you can see that we provided different demonstrations, and when we go outside the region of the demonstrations, the variance starts increasing, the uncertainty of the robot starts increasing, and added to these extra terms create this stabilization field. So this was all the introduction about the theoretical background of the paper. For more details, please refer to the manuscript of the work. And now I will give the word to my first co-author, Anna Mazaros, that is going to give you more details about which type of experiment we performed, and in particular why we did this choice.
In the first experiment, we look at the task of pulling a plug and bringing it to its desired location. The focus of this experiment is on observing the effect of providing a single demonstration versus giving multiple demonstrations. When providing demonstrations, we may want to move only along one specific trajectory. If we give a single demonstration, if you look at the image on the right-hand side, you can see that thanks to the minimization of the epistemic uncertainty, the policy will aim to redirect the robot back towards this desired trajectory. But of course, we can perform a task in many different ways. It may not matter so much which trajectory the robot takes, as long as it brings the plug from point A to point B. And we can show this by giving multiple demonstrations. If you look at the image on the left, by giving multiple demonstrations, we broaden the region of certainty. And this allows the robot to adapt freely to perturbations within this region, but at the same time it avoids the robot from being brought outside of this region and into the unknown region. The second task is pushing a box. In this experiment, we took a closer look at the reasoning of applying force through the control of both stiffness and attractor, instead of only learning the attractor. On the left, you can see the setup as well as the attractor field, with the yellow region denoting the region of higher force, in other words, the region in which the robot is pushing the box. However, we're considering that the robot may come across interactions with people, and it may happen that a person, for example, suddenly removes the box midway. Now, if we're only learning the attractor, it can happen that we need a large attractor distance in order to be able to push a fairly heavy box. And if the box is removed in such a case, we end up with fairly high velocities as a result, which are denoted in red in the right-hand image. If instead we limit the maximum attractor distance and instead increase the force through a further increase in stiffness, we're also able to limit the velocity in the case that the box is removed, which is denoted in blue. This in turn also limits potential impact forces and improves safety. Next, we look into periodic manipulation tasks, such as board wiping. Aside from enabling periodic motion, this task brings with it a further challenge. Since we don't have a force sensor, during the demonstrations we cannot observe the desired forces that have to be applied onto the board. As a result, the robot only learns that it has to move across the surface of the board. However, if we want to apply force perpendicularly to the direction of motion, we have to provide teleoperated corrections in order to be able to successfully clean the board. In the image in the middle, between points A and B, you can see the effect of such corrections. Meanwhile, thanks to the minimization of the epistemic uncertainty, the robot remains close to the trajectory, thus avoiding divergence and enabling a periodic motion. Another aspect that was tested in the case of board wiping was adapting a learned policy to new constraints in the environment, such as an obstacle. If something changes in the environment, you don't want to have to provide a new demonstration and corrections every time. With our proposed approach, you can adapt the policy online using only corrections. The way this works is that you first begin with correcting the policy within the known region, and if you end up going outside of this known region, we add new points. This generates a new known region, but also enables a data-efficient learning of the policy, since new information is only added when it is necessary, and otherwise prior knowledge is merely corrected. Finally, since our framework is supposed to allow people who don't necessarily have a background in robotics and machine learning to teach even challenging tasks such as inserting a plug, we conducted a small user study with 15 participants. The participants were given a couple of minutes to get familiar with the setup before the official trial, and they only needed a few minutes before they were able to successfully train the task. On average, they needed 1.5 minutes, and this is including both the time needed for the kinesthetic demonstration, as well as any amount of correction rounds needed before the robot was able to learn how to insert the plug. Of this, only a few seconds of explicit corrections were necessary, and they were mainly around the point where the robot had to insert the plug, since they had to give minor corrections for the precision part, as well as increase the force to be able to successfully push the plug in. To conclude, we introduced a non-parametric and interactive approach for learning reactive policies for different kinds of force interaction tasks from humans, regardless of whether they are experts or are using such systems for the first time. The ILoSA framework can be used for both goal-oriented as well as periodic movements. Finally, ILoSA demonstrated reliable trajectory execution, as well as learning policies in a data-efficient and user-friendly manner. In future works, we aim to look in 3 main directions. The first takes into consideration that usually the tasks that we perform consist of multiple subtasks. Therefore, we aim to investigate how to learn the sequence of these subtasks and incorporate this into our framework. Secondly, the learned policies within this work were all with respect to a global reference frame. However, if we consider tasks such as assembly, where we have to grasp objects and bring them to different locations, it makes more sense to learn a policy which adapts with respect to a particular frame, such as that of the object or goal. Finally, when providing kinesthetic demonstrations, we as people tend to be quite slow. Therefore, another work will aim to investigate how to modulate the velocity through corrections in order to achieve superhuman skills that we are not able to physically demonstrate. With this, we thank you for your attention and look forward to answering any questions that you may have.